Good. So, okay, question. So last time we quite quickly went through what happens when you consider dynamics of an isolated system that is integrable and what you should expect for the stationary state. Now the question we want to address is, today is a bit more general, generic, and it is, imagine that we have a generic system that is not integrable. The only constant of motion is energy, so that's what we have typically, unless we do some fine-tuning. And the question we have is, what should we expect for stationary state in this case? Now, this is not, of course, not a question that is important only for quantum systems. It's also a question that has been studied in general for classical systems. I already told you that there were some numerical experiments by Fermi, Pasta, Ulam, and Jingu on anharmonic chains, so essentially chain of harmonic oscillators perturbed by a quartic term. And what they wanted to see there was whether you could observe equipartition of energy in the stationary state, and it was not observed. So that was a quite interesting observation that led to a lot of research in over the years. So now what we want to do is figure out what is a working notion of not much equipartition, because as you know, equipartition is something that pertains only to harmonic systems, but of thermalization for quantum systems that are both out of equilibrium but thermally isolated. Of course, I mean, if you couple your system to some external, the reservoir is always going to thermalize, and you know how it happens. So let us try following the principles that you learn in elementary statistical mechanics courses. One thing that you are told is that all statistical mechanics is built starting from the equal a priori probability postulate. That tells you that if you're in a thermally isolated system and you have an average energy, that is your only constant of motion, so the only information you have about your system, then all microstates that are consistent with this average energy up to some tiny fluctuations delta will be equally probable. Now, in a quantum mechanical setting, you write this by saying that rho microcanonical is equal to a linear superposition of all states n whose energies are between E and E plus delta. And you will have 1 over gamma phi. Gamma phi is essentially the number of states within this energy shell, and the energy in this case. So this is the equal a priori postulate of statistical mechanics. Now let's ask ourselves a question which is a bit more practical than this. Imagine that we have a thermally isolated system. We give it some initial energy, so we have some average initial energy density, and we kick it out of equilibrium, and then we go to the stationary state. And we ask ourselves, will this ever be the stationary state of the dynamics? So, in order to answer this question formally, let me define. So I just gave you the information that I will give some initial energy density to my system. So let me start with some microcanonical, what I call a microcanonical state, which is a generic state which is a linear superposition of states within the same energy shell with some coefficients that I don't know in general, some CNs, some complex coefficients. Right, so of course, I mean, I have to take superpositions within this energy shell, otherwise I will never ever go into a stationary state of this type. Right, so now I time evolve this state with my Hamiltonian H, of which these guys are eigenstates. So this is the eigenvalue equation, and I look at the density matrix that will describe the stationary state for, you know, all observables I can think of. And we already know the answer to this. This is going to be the diagonal ensemble. So the diagonal ensemble is going to be the sum over n between En and E plus delta of Cn squared. So this is the stationary state and density matrix. It's something that we figured out. Now, notice that here, well, what I'm assuming is that E is some average energy density, which is usually in statistical mechanics assumed to be extensive, right? So this is important for equivalence of ensembles, so it's going to be proportional to the volume. And of course, the delta, right, if you think about, so one way I could generate a state of this type, for example, is by doing quenches, right? What I've been talking about in the previous lectures. So you imagine you have a system that depends on a certain, the Hamiltonian depends on a certain parameter, and you change this parameter everywhere in time at some initial time in space, right? And then you ask yourself, okay, so what will be the initial state in the representation of the eigenstates of the final Hamiltonian? If you think about what we did in terms of work statistics, I told you that work statistics for a global quench, you will have some average work that is extensive and some fluctuations that scale as, you know, relative fluctuations that scale as 1 over square root of the volume. So this translates to the fact that this delta, if you think about it, so I'm not explaining it very well, so, but you know, you have all the tools to figure it out by yourself. If you do a quench, in practice, you will go into a superposition of this type where delta scales like square root of volume, roughly. So it's subextensive, and therefore it's a pretty well-centered superposition. Anyway, so the question now is, can this ever be consistent with the equal a priori probability postulate of all books you love in statistical mechanics? And the answer is, of course, not, right? Because if you think for a second, in order to have this equal to this, you should have that absolute value squared. This is uniform and equal to the inverse of the number of states within this microcanonical shell. So all these coefficients should be equal up to a phase. And this does not make any sense. I mean, this would be very restrictive. It would be telling you that if this was what we pretend, so if this is what we pretend for a system to thermalize, that would mean that the only way to get a thermal state would be to have linear superpositions with uniform coefficients up to phases. And it's very restrictive. You would have to prepare your initial state very, very nicely, right? It's not enough to know what is the average energy density of your initial state. So it cannot be. Cannot be. I mean, this is a too restrictive notion of thermalization.
Sorry.
Yes.
once again, this energy shell that we're discussing.
Yes.
Once again, what is it, or what is E here?
Right. So how do you introduce a microcanonical ensemble? Go back to when you were 15 years old. I don't know when you were.
Okay.
When you were 10 years old.
Okay.
So how did you introduce a microcanonical ensemble? They told you. So you have a closed system. You know what is the average energy of this closed system because energy is the only constant of motion that you have. So and therefore you pick your phase space. Typically this is done for a classical system. You pick your phase space.
Yes. Okay.
And then you draw an equal energy surface on this phase space.
Okay.
And now you use the equal a priori probability postulate of statistical mechanics that tells you that all microstates that are consistent with a macrostate are equally probable. Right. But then the problem is that when you do the classical case, the PDP, the surface would be volume 0. And in order to have to define the volume so in order to define what is the volume of your equal energy surface, what you do is you give it a small thickness, delta, which is subleading or very small as compared to the energy that is extensive, and then you compute on this lasagna or whatever pancake, you compute your phase space volume. And from this phase space volume, you essentially construct all statistical mechanics, right? Because then the entropy is equal to minus log of phase space volume, etc., etc., etc.
Yeah. I mean, so
here
this is rho at this given energy E, which is first integral of the whole system.
Yes, absolutely.
Okay.
So what I'm doing here is the same construction that is being done typically for classical system, for quantum system. If you take a book by Wang, this is how it is introduced. I don't remember Landau-Lifshitz, to be honest. I never read StatMech of Landau-Lifshitz.
I mean, I only want to ask a very simple question. So this is very specific state which corresponds to this total energy E, and that's it. Very specific quantum state. Okay, perfect.
So what I'm saying is that if you use the equal a priori probability postulate and you apply it to a quantum system and you assume that all microstates, so all eigenstates within the microcanonical shell are equally probable, then you come up with a microcanonical density matrix that has this form. But then I'm saying, if you go to the stationary state of a generic evolution starting from some state that linear superpositions within this microcanonical shell, you will never go to the stationary state like this. This is too restricted. And then the question is, then what does it mean to termalize? I mean, it cannot be just this. And this was a question that was addressed by a number of people. Quite surprisingly, two guys in the 90s, Deutsch and Srednicki, came up together with a possible ansatz to, or possible hypothesis to define termalization in a quantum system. Can I erase? So, what is the story? So we go back to, in order to understand what they did, we have to start thinking as experimentalists. This is always a very good idea in physics, right? So it's a bad idea to think directly as a string theorist. It's a good idea to think directly as an experimentalist, because it keeps you down to earth and then you start computing things that can be measured. Right, so if you are an experimentalist, imagine that you're doing experiments with cold atoms or with ion traps or whatever you want, some thermally isolated system. How would you define thermalization? Well, one way to define, you don't measure density matrices. Density matrices, you can obtain them by tomography, but it's a very complicated thing. You can do it only for small systems. Typically, what you measure are observables. You measure observables, you measure correlation functions of observables. So, one way to define thermalization could be to say that I want that the limit for time going to infinity of the expectation value of my favorite observable, or some local observable, or of all local observables. Why local? Because all observables that matter in physics are local observables. Which is equal, as we all know from previous lectures, to the time average of O of t. So I wanted that this is equal to, or infinity, to be equal to trace of rho microcanonical O. So I want that the stationary state value of this expectation value of this will be identical to the microcanonical thing. And if it is, if it is a system with a local Hamiltonian and this is a local observable, then the fact that it's equal to the microcanonical will imply that this is equal also to the canonical and ground canonical, right? Because of equivalence of ensembles. So you know that, right? So this is requirement number one. But it's not enough. It's not enough because, this is a constraint just on expectation values, but it's not a constraint on dynamics. And there is a second constraint that typically people looking at thermal equilibrium look at, which is the fluctuation dissipation theorem. The validity of the fluctuation dissipation theorem is a signature of the fact that you are dealing with a system that is in thermal equilibrium. So, how do we define the fluctuation dissipation theorem? Let us pick our favorite observable. Let us define the correlation function, the response function. And let us define the symmetrized noise correlator. Oops. Where delta O means O minus the average of O, right? So this is now, in general, if I'm considering, for example, quench dynamics, so this average means average with respect to some initial state, then it is clear that these correlation functions will not depend just on time differences, will depend on the two individual times, right? Because it's not a time translational invariant situation. So I've been tempted to scroll it. So the idea to define the stationary value correlation functions is the full angle. You take these two times, t and t prime, and you change coordinates, timed coordinates, you go to the so-called Wigner coordinates. One is the average time, t plus t prime divided by 2, and the second one is the time difference, t minus t prime. Okay? And then you take the limit for the average time going to infinity. So that will correspond to the stationary state. So, in other words, let me write it here. I'll take chi of t tau, and I'll take the limit for t going to plus infinity, and this is chi infinity of tau. Is essentially as if I mean, if you think about it, it's as if you let your system relax to the stationary state, and then once you go to the stationary state, you measure your correlation functions. And of course, since it's a stationary state, your correlation functions will appear to be translational invariant, right? Because time translational invariant, so will depend on time differences. So that's exactly what is being done. Of course, I mean, you can obtain this by doing the averaging over t, the time averaging over t of the full correlation function. We will do it later. Another thing you can do is do the same for the symmetrized noise correlator. And now, the fluctuation dissipation theorem is a relation between the Fourier transform of the symmetrized noise correlator and the Fourier transform of the response function. In equilibrium, you want to have that S infinity of omega is equal to 2 cotangent hyperbolic of beta omega over 2 chi double prime of omega infinity, where chi double prime is so chi of omega is equal to chi prime, which is the real part, plus I double prime, which is its imaginary part. Okay? So this is the fluctuation dissipation. So typically, if you are an experimentalist and you want to figure out whether your system is in equilibrium or you want to have some reasonable signatures of whether your system is or isn't in equilibrium, what you will do is check whether expectation values of correlation functions correspond to this, and you will want also to check whether the fluctuation dissipation theorem is satisfied or not. Okay? That's it. Another question is, so all of these requirements are requirements not for states, but for operators, right? You see that, I'm looking, it's as if the operator was my glass through which I'm looking at the state, right? So I'm looking at the state through the operator by measuring the properties of a certain observable. Another question is, so what are the requirements on the system that I need to have in order to observe 1 and 2? And here come these two guys, Deutsch and Stretnicki. Can I erase this? Who said, well, since we are talking about operators, they proposed to describe thermalization in terms of a certain hypothesis, or if you want postulate, or whatever, you name it, for the matrix elements of the operators in the energy eigenbasis.
Sorry?
Yes?
Is there a reason why we are looking at the response of expectation value of operator O to itself? So when we have O
Okay,
correlation.
this is a very, very good question. Of course, I mean, you could look at the response function of a certain observable to some operator, to some perturbation that is linearly coupled to some other observable, right? So that's what you're asking.
Yeah.
And, right, so in that case, you would have to generalize all of this. It's not a big deal to do it in equilibrium. I mean, all these identities, you can prove them just by Lemon representation, so it's not a big deal. The question is, the point is that rephrasing the eigenstate externalization hypothesis that I'm going to write now, for the situation in which you have two different operators in the correlation function is slightly complicated, right? So I know only one paper that attempted to do it. I can figure it out and give it to you, but it's not very, I didn't understand fully what they were doing. So the full answer is, I know how to do things for correlation functions, for response function with the same operator. With two different operators, it's complicated. Okay?
Yeah.
So it's a good question. Okay, so just a tiny bit of history. The eigenstate well, let's write the eigenstate determinalization hypothesis, and then we'll leave the history for next step. So imagine that, so let me define O and M as the expectation value of the operator in the energy eigenbasis of my Hamiltonian, right? So N and M are eigenstates of energy En and in M. So the eigenstate determinalization hypothesis states that whenever these matrix elements can be represented in this form, then thermalization in the sense of 1 and 2 that I mentioned before will occur. So in this form, let me first write it and then I'll explain it. Okay, so I have this matrix elements. The statement is there exist two functions, one function O of E and another function F of E and omega. These are functions of E, which is En plus En divided by 2, and function of omega equal to En minus En. And so essentially the diagonal matrix elements of this matrix are represented by given by a smooth function, smooth function of the energy, of the average energy. This is statement number 1. Statement number 2, the off-diagonal matrix elements are represented in this form where S of E is the microcanonical entropy, so minus the log of the number of states within a microcanonical energy shell centered around E and of size delta. And Rn and M is a random function, pseudo-random function, zero average and unit variance. So let me stop for a second on this statement. Well, if you have the matrix elements of your given observables, and you want to check whether the diagonal matrix elements are given by a smooth function of energy, you just do your exact diagonalization and check whether you have a nice smooth interpolation of your diagonal matrix elements that depend only on the energy or not. Right? So this is statement number one. Typically, for systems that satisfy the eigenstate thermalization hypothesis, you will see that your diagonal matrix elements center or cloud around some smooth function and nothing else. The off-diagonal matrix elements, in addition to this guy here, that is essentially 1 over square root of the number of states. So it's a normalization factor. And a smooth function of the energy and of the energy difference will have also this statistical factor. This statistical factor is essentially incorporating the idea that if you pick all your energy levels within a microcanonical shell, so there is an average energy density that is extensive. There is a width delta. The width is such that inside here there are exponentially many levels, right, in the thermodynamic limit. And now I take statistics by fixing the energy difference and moving this around, and I pick all, within this microcanonical shell all states n and m that have a fixed energy difference. Well, the statistics of this off-diagonal matrix elements can be represented by this function with 0 average and unit variance. Okay? So all I'm trying to say is that statistics will be taken within some coarse-grained microcanonical shells. So this is in practice how a guy is doing, like the guy who played a big role in checking this numerically was Marcus Riegel, and he did a lot of studies of exact diagonalization with pretty big system sizes, well, 26, 28, so not huge, but still reasonably big for non-integral systems. And taking statistics this way was able to check that indeed for systems that are expected to thermalize, you will see that the statistics of your matrix elements can be represented in this form. Okay?
So this is numerical result.
So you should put it differently. If I assume that the matrix elements of my local operators all satisfy this, then I'm able to prove analytically, and I will do it in a second, that 1 and 2 are satisfied. Okay. Then you could ask yourself, how do I prove that my local observables for my favorite spin chain or favorite electron model satisfy this? Well, you do exact diagonalization and you check what I told you.
Yes.
Okay, so it's a numerical, it's always a kind of numerical result to prove that some system satisfies the eigenstate thermalization hypothesis.
So numerically they just solve like evolutionary problems and just check.
Sorry?
So numerically they just solve evolutionary problems?
No, don't solve the evolution, do the exact diagonalization.
Yes,
you find
exactly.
eigenstates, you compute matrix elements, you check this.
Yeah, okay, yeah, thank you.
Okay?
Yeah.
Okay, so
Yes.
if this condition on the right board is fulfilled, then the
Is fulfilled in certain systems. If this is fulfilled, then thermalization in the sense 1 and 2 follows.
Yeah, but does it also go in the other way? That,
Okay.
if
This
you
is
give
again
that,
a good question. No, I don't know. The answer is I don't know.
Okay, so if
And
we-
I think Okay, we will discuss it later. There are some very subtle points here. I mean, the fact that this has a smooth function is a pretty strong constraint on whether your system will be. What is that? So it's a pretty strong constraint on the fact that thermalization in sense number one will be satisfied. What you could ask is whether also this second thing has to be always satisfied. And what you can play with is the statistics of R. So I will discuss it later on. There are some complications here. Yes?
Also got a question, like when I look at the left side of this equation, I think about something in quantum mechanics like hydrogen atom, something in matrix element or perturbation of matrix element. But I never saw in quantum mechanics what I see on the right side that there is some random variable which has some averages. So what is the origin for you? Because
Okay, so here we come back to history. So this eigenstate thermalization hypothesis originates from a community of people working in quantum chaos. It was invented in the 90s by Deutsches Radnicki, who had mainly in mind billiards and chaotic systems. And they were asking themselves the question of what it takes for a quantum system to be ergodic. Now, there was a conjecture that was put forward by Michael Berry a few years before this, that if you have a billiard or in general system in which your eigenstates are quantum chaotic, then if you try to represent statistically in the way of random matrix theory, right? What is the typical eigenstate of your system? It's going to be a random superposition of all possible plane waves, which are consistent with the average energy density, with pseudo-random coefficients. So it was essentially thinking in this way. It was picking states within shells and taking statistics within these shells and asking what is the statistical appearance of eigenstates within microcanonical shells. And well, this is another way to formulate essentially in the spirit of random matrix theory this question, right? So, you could what I'm trying to say is that you could ask the same question. What that you're asking is, for example, when you want to check using random matrix theory whether a system is chaotic or is integrable. How do you do that? You diagonalize it within a certain symmetry sector, and you check, once you do the unfolding, whether the level statistics is Wigner-Dyson or is Poisson. If it is Poisson, it's integrable. If it is Wigner-Dyson, it's not integrable, it's ergodic. And how do you do that? Well, you do the unfolding, which is essentially corresponds to normalize everything by the density of states, and then you compute the level statistics. So you look at different level spacing and you compute the statistics of level spacing within the central part of the spectrum, roughly. So also in that case, I mean, you're looking at the spectral properties of your system in a statistical sense. So here we are looking at the eigenstates, at the matrix elements of local observables in your system in a statistical sense. If this is satisfied, then thermalization occurs. If this is not satisfied, then it doesn't. That's it. So it's in the same spirit. Other questions? Okay. So now the question is, what do I do with this? And so what I have to do is to prove that given this eigenstate thermalization hypothesis, then if this is satisfied, so if you have your favorite system, you do your exact diagonalization and you check roughly that this is true. There are some other caveats about fluctuations, but never mind. You check that this is true, then this is going to be enough to prove that your system thermalizes in the sense 1 and 2. So let's see how this follows. Well, step number 1. Let's take the limit for t going to plus infinity of O of t. Well, we know that this is given, we have done this calculation by the trace with respect to the diagonal ensemble of O. This is sum over n Cn squared O and n. But now O and n is essentially O of E. So this is equal to sum over n Cn squared O of E, where E is En plus En divided by 2. Now, if this is a smooth function, smooth where? Smooth on a scale delta, right? So which is this tiny thickness of my microcanonical energy shell, then I can safely take this out. Well, this is normalized to 1, and then I have that this is equal to O of E, which is of course the same thing that you will get if you will sum over a microcanonical density matrix. Sorry, not sum, phrase. So this first part is always disappointing because, you know, I remember many years ago when in the 2008, 2009, when we were discussing this in the community, you know, people were saying, okay, but this is trivial. I mean, you're just saying that if this is a smooth function, then you can take it out, and of course, I mean, you will have that the average is equal, so the microcanonical averaging is equal to the averaging with respect to the diagonal distribution, because essentially everything is centered in a microcanonical shelf with delta. Super triviality. And indeed is not that complicated, this part. I mean, it's a sort of, this first diagonal ETH is a sort of tautology. Let me put it this way. It thermalizes if it thermalizes. What is non-trivial is the off-diagonal part. The off-diagonal part is really quite non-trivial, and it took me some time to appreciate this. So let me show you why it is non-trivial. So the off-diagonal part is what controls essentially the behavior of correlation functions. Let's start considering this matrix element. So imagine that now the state with respect to which we do the averaging is again a microcanonical superposition. So it's sum over alpha and beta. Alpha and beta are taken within a microcanonical shell of C star alpha, C beta, and then alpha O T, O T, T. And this is equal to sum over alpha, beta, and gamma of C star alpha, C beta, and then, okay, here I'm putting a resolution of the identity inside here, and then I'm expressing the time dependencies, and I will get e to the I E alpha minus E gamma t e to the I e gamma minus e beta e prime o alpha gamma o gamma beta. Okay? And then, where these are, okay, you understand these are matrix elements. So now, what do I do with this? If I want to get something, to get some idea about whether your system is thermalizing or not, I have to go to the stationary state. So I have to pass the Wigner coordinates, and I have to do the time averaging with respect to the average time to look at the limit for t going to infinity. So I pass the Wigner coordinates, and this will be alpha, beta, gamma, c star alpha, c beta, e to the I, e alpha minus e beta, e, e to the I, e alpha plus e beta minus e alpha plus minus 2 e gamma divided by 2 tau. And then I will calculate the segments. Alpha gamma. Now I take this and I do the time averaging with respect to the variable t. Assuming that my spectrum is non-degenerate, which by the way, for non-integrable systems is a quite reasonable assumption, then doing the time averaging will speak out for me a delta alpha beta. Okay? You agree? And therefore, I will get that this is equal to the sum over alpha, c alpha squared, o alpha gamma, o gamma beta, e to the I, e alpha minus e gamma tau, and that's it. And this is, of course, equal to the limit to t going plus infinity of average of all t plus tau over 2 over t minus 2.
Sum over alpha gamma, and it is
Alpha gamma.
alpha gamma,
Yeah,
alpha gamma, alpha.
Gamma, and this is
Yes,
gamma
yes,
alpha.
yes.
Thank you. Okay, so now that we have this, we can use the eigenstate thermalization hypothesis, and you will see how it works. Essentially, we will plug in here the fact that this is O of E delta alpha beta alpha gamma plus e to the minus s e alpha gamma over 2 f e alpha gamma over alpha gamma r alpha gamma. I will plug in here this expression, and then the trick is I do the averaging with respect to the statistics of this. So I assume that it's a pseudo-random function and they average over its statistics. Okay?
So, two questions. First, very, very naive, but would take the limit t to infinity,
Mhm.
right? And in the same time, we said this is like an average over t. Right? I mean,
Because
It feels
I
like
might-
this is it should give the same result, but for
No, you remember, we did it.
Yes.
We did
okay,
it
yes,
that
yes,
if the
yes,
limit
yes,
exists,
Yeah.
then the limit for t going to infinity and the time averaging are identical.
Yes.
Or at least I didn't prove it, I just mentioned it.
Yes, we discussed.
But it is true, you can check it by yourself.
Mm-hmm.
If the limit exists, it coincides with the time averaging.
Second question.
Yes.
You keep saying that this is like pseudo-random functions.
Yes.
Right? Why pseudo-random?
Well,
what is so
so
special
I'm-
about their statistics?
You know, at the moment, I'm just assuming that it's a random
Yes,
function.
exactly.
So I'm saying it's pseudo-random in the same sense that, well, I should say it also for random matrix theory, right?
Okay.
You know,
Fair enough.
so in the sense that it's, you know, the statistics is inferred by taking averages, by looking at, by coarse graining your system into shells and taking statistics within those shells.
You mean like
Right.
the origin of randomness? Is
Yeah,
like
the origin of randomness
But
is-
of course, great. Okay.
Yeah, it's
okay.
let's remove the pseudo, it's random.
Okay.
It's random. Okay, so it's random and I take the average with respect to the statistics of R, of this statistical factor. Now, this average will kill all terms in which there is one of such guys multiplied by one of such guys. Here I had two, right? Why? Because the average of R is equal to 0, and I need at least two of them in order to get unity. So if you use the fact that R alpha gamma average is equal to 0, R alpha gamma is equal to 1, then you will be able to do this. I want you to notice something. Notice that in order to do this averaging, I don't have to assume anything about the average of objects like this.
Mm-hmm.
Right? I'm not assuming anything about correlations between different matrix elements. I'm just looking at the statistics of single matrix elements, but not at the correlations between different matrix elements. This is a crucial observation, it's very important. Anyway, so once you do this, you will get that this is equal to sum over alpha, C alpha squared, over 3 squared plus sum over alpha and gamma, C alpha squared, e to the I, E alpha minus E gamma. Tau F alpha gamma, F gamma alpha times e to the minus s e alpha gamma. So here I'm using the notation, so this guy here is this. It's just a shortcut notation for this. E alpha gamma is E alpha plus E gamma divided by 2, and omega alpha gamma is E alpha minus E gamma. Okay? This is the notation I'm using. Right. So, good. Now we are essentially ready to, so this was for the matrix element of T of prime unit for T going to plus infinity and averaged over the statistics of the level statistical factor. something, well, whatever. Now, using this and its opposite, t prime t, I can easily compute correlation functions and response functions, okay? Because one is the anti-commutator, one is the commutator. And what I will get is this. Oh. So I'm going to write the answer, but it's not hard to get it. 2 tau t tau tau sum over alpha and gamma c alpha squared sinus of omega alpha gamma tau times e to the minus s e alpha gamma times the absolute value of alpha gamma squared. And similarly, I will get that s infinity of omega is equal to 2 sum over alpha and gamma c alpha squared cosine of omega alpha gamma tau e to the minus s e alpha gamma alpha gamma squared. Okay, so now all of these, S, the entropy, F, the cosine, the sine, etc., are all smooth functions of their arguments in some mathematical sense that I'm not going to specify. Hello, smooth. So, and here, when I sum over alpha with these coefficients are non-zero only within a microcanonical shell. So I can perform this summation just by setting sum over alpha C alpha squared equal to 1 and replacing everywhere instead of E alpha the average energy E, up to subsequent terms that will be proportional to delta. Okay? So let me do this. How do I do it?
I mean, so they're just smooth in comparison to the distance between the levels.
Yeah, I mean they're smooth on a scale delta.
Yeah.
So if I do so, then 1 will become equal to 2 theta tau sum over gamma sinus of E minus E gamma tau e to the minus s e plus E gamma divided by 2, and then f of E plus E gamma divided by 2 E minus E gamma squared. And something similar for the other, right?
Mm-hmm.
So it's not a big deal. I don't think I have to do it. Right, so let us stick to this, which is chi. So now I can replace this summation with an integral. I will have just to put the density of states, right? And let me do it explicitly. I will get that this is equal to 2 theta of tau times integral dt gamma over delta times e to the s of t gamma minus S of E minus E gamma. Sorry, E plus E gamma divided by 2. And then F of E plus E gamma divided by 2 E minus E. And there is a sinus. So why this? Because here I would need to, so when I do the summation over gamma, I can write it as integral over dE gamma of the number of levels within a microcanonical shell centered around the gamma divided by delta, divided by the, the size of the shell. This is the density of states. And now N of E, I can represent it as the exponential of the microcanonical entropy, right? So this is equal to integral dE gamma over delta of Es of E gamma times something. So that's what I'm doing. Right, so now we're ready to simplify further things, because we take this and we change variables. We write it, so we call E minus E gamma omega, and then changing variables here, we will get integral d omega. Okay, this I can erase. E omega over delta e to the S E plus omega minus S of E plus omega over 2 times 2t of tau sin of omega tau times F of E plus omega over 2 omega squared. Okay? Okay, so now comes an important assumption. Not assumption, observation. So if O is a standard operator that you use in many body physics, what are known as few body operators. If you think about the density, magnetization for spin chains, any local observable that you can think of, this is always going to have matrix elements, if you have a local Hamiltonian, between energy eigenstates that differ not by extensive energies, but by intensive energies. So an operator like sum over sigma x I, right? So this is going to have matrix, if I have a spin chain, this is going to have a matrix element between a state like this and a state like that, right? But it's not going to have, and these two states typically differ by just a few links that are broken, so just by an intensive amount of energy. But it's not going to have matrix elements between eigenstates that differ by extensive energies. Okay? This is typical of what are known as few body operators. This is an example of a few body operator. If instead you pick an operator like this, product where I from 1 to L, sigma I x. This is not a few body operator. It's a collective operator. It's the product of all sigma x everywhere. This is flipping all the spins altogether from the first to the last, and it has matrix elements potentially between states that differ by an extensive amount of energy. But this is not the state you typically look at in many-body physics, because the state, the observables you look at in many-body physics are sums of local operators. All right, so the fact that sums of local operators have matrix elements between states that differ only by an intensive amount of energy implies that the function f of E and omega goes to 0 as omega, when omega becomes much larger than an energy scale, which is such that is subleading with respect to the energy and the scaling with system volume. So this is extensive, this is sub-extensive. So this goes to 0 as V goes to infinity. Okay? So all of this just to say, this decays fast with omega. I'm phrasing it in simple terms. This decays fast in omega on a scale that is much smaller than the energy E, that is extensive by assumption, and therefore I can take all these functions and do a Taylor expansion in omega. Okay? This is the statement. All of this mumbo jumbo to say something simple. Okay, so now let's do the Taylor expansion. S of plus omega minus S of E plus omega over 2 is equal to, if you do the Taylor expansion, to omega over 2 ds dE. But the SDE is one of the over the inverse temperature, right? In thermodynamics. So is one over the temperature. So this is beta omega over 2. And we can of course roughly state that this as such. Okay? Now, if I take now these two expressions, I plug them in here, and I do the Fourier transform with respect to tau, and all of you know how to do this Fourier transform, so I don't have to do it myself. Then, can I raise up here? Then what I get is that chi infinity of omega is equal to minus integral d omega prime over delta of e to the beta omega prime divided by 2 f of e omega prime squared plus minus e to the minus beta omega prime divided by 2 f of e minus omega prime squared divided by omega minus omega prime plus e plus. Now notice that I'm writing it here. F of e minus omega is equal to f of e omega star, if I assume that my states are non-degenerate. right? And therefore, well, here I can just put a plus. So if I can put a plus there, then, then what I will get is that, right, so you take this, and what I need is chi double prime, which is the imaginary part of this function. The imaginary part, I take it by using the Cauchy formula here. So I use 1 over prime plus equal to principal part integral 1 over minus I5 delta. I plug it in here, I do the integration, and I will get that this is equal to 2 pi over delta sine of beta omega divided by 2 f of e and omega squared. I can of course do something similar for the symmetrized correlation function. I didn't do it, but of course, I mean, you just have to repeat the same passages. Yes.
Isn't it the hyperbolic sinus?
Yes, it is an hyperbolic sinus. You're right. Sorry. Okay, so I can repeat the same calculation for S of omega, and I will obtain 4 pi over delta cosine hyperbolic of beta omega over 2 f of e omega squared. And therefore, you see from these two expressions that when combined together, you will get this. Okay? Where the inverse temperature is just obtained by the thermodynamic formula, right? Derivative of the microcanonical entropy with respect to the energy. So now you understand also why that normalization factor in the off-diagonal matrix elements. Okay? So this is, I don't know, I mean, the first time I re-derived this, I was very happy. I don't know about you, but it's actually very deep. It means that one could write a book of statistical mechanics. If one would want to be very sophisticated, one could take a book and write statistical mechanics starting with quantum statistical mechanics and using, instead of the equal a priori probability postulate, just this. And everything else will follow, practically, more or less. In particular, one thing that will follow, if you think for a second, is that the von Neumann entropy in the stationary state has to coincide with the thermodynamic entropy. Why? Because if I consider all local observables concentrated in a certain subsystem A, and I assume that for all these local observables, the eigenstate thermalization hypothesis is valid, then in practice I will have that for all these local observables concentrated in A, the expectation value with respect to the diagonal ensemble will be equal to the expectation value with respect to the microcanonical ensemble, that is equal to the expectation value with respect to the canonical ensemble, because of equivalence of ensembles in systems that have extensive energies, etc., etc., etc. And this will imply, in practice, that my reduced density matrix of A is practically, for all purposes, identical to e to the minus beta h concentrated on A divided by its associated partition function. So which means that when I compute the von Neumann entropy for the entanglement entropy of A with respect to B, I will obtain that this is minus trace rho A log rho A. This is equal to the canonical entropy of my system at inverse temperature beta. So it's going to be extensive, and it's going to be indistinguishable from the thermodynamic entropy. Now, there is a subtlety here, that this is true also for integrable systems, by the way. So if you take a typical, if you take a high energy state in integrable system, or if you do a quench in an integrable system, unless you have long range interactions, you will go to, so your entropy will go to a stationary state in which scales with its volume like. The area law or logarithmic is true only for ground states. I mean, it's valid for low energy states. But in any case, it's indistinguishable from the thermodynamic entropy. So, therefore, one question that we will be addressing in the second, after the break, is a question that was asked by Alexei Kitaev first. And it's actually a very interesting question, in my opinion. Well, he was interested in black holes, never mind. But my reformulation of the question is the following. Imagine that you have a thermally isolated system that is in a fully coherent quantum state that is a stationary state of the dynamics for which we see thermalization, right? In this sense. What should we do or should we measure in order to see that this is a coherent state and not some incoherent density matrix, some mixed density matrix? What kind of experiments should we do in order to see this? Now, later on we will be discussing both the proposal by Alexei Kitaev, which is to look at some quantities that are called out-of-time order correlation functions, or another possibility, which is to look at entanglement, which is what is being looked at by the entanglement of the von Neumann entropy, in a different way, focusing on multipartite entanglement. In both cases, you might get information that is beyond the eigenstate thermalization hypothesis. Now, since we have another few minutes, I can comment also on what is observed in real systems. Now, in real systems, typically the eigenstate thermalization hypothesis is, let me put it this way, is satisfied for most eigenstates, but sometimes is not satisfied for all eigenstates. There are certain eigenstates that are peculiar, and one example is are the eigenstates of this model. Which is called PXP model. It's a model that essentially represents or describes something that is known as Coulomb as, not a Coulomb blockade, as, well, some kind of blockade. Let me describe the physics. The P's here are projectors. So P is 1 minus sigma Z I divided by 2. So if one of these guys is pointing up, either this one or that one, then the operator X cannot act. Okay? So it means that if you take 3 spins and one of these guys is pointing up, this guy cannot be flipped. So if it was down, it remains down. Sorry. If it was up, remains up. If it was down, remains down. Right? Now, this model here is not integrable. Most eigenstates satisfy the eigenstate determinalization hypothesis. If you look at local observables, they satisfy eigenstate determinalization hypothesis, with the exception of a set of size for the n, or for the L. L is the system size of eigenstates that are known as quantum scalars. You can derive them by yourself, just taking this model and doing exact diagonalization. So these quantum scalars eigenstates have the property that area length entanglement entropy. They are they have a large overlap with the L states, and that's it, essentially. So how were these guys seen? There was an experiment some time ago in Misha Lukin's group at Harvard, in which they took an initial state that was essentially an L state, and they wanted to look at the dynamics of this system. And what they saw is that it essentially had a collapse and revival between the two flipped L states that continued for a pretty long time. While, since this Hamiltonian is not integrable, you would expect it to decay to some stationary, ergodic value pretty quickly. And, well, you can describe this persistence of oscillations just by considering the overlap of this guy with this subset of states, these car states that are non-ergodic. Right, so all of this to say that, thermalization, if you take a system, most of eigenstates are satisfy the eigenstate determinalization hypothesis. That might be a sub-extensive set of eigenstates that does not. In this case, you call it weak ETH. I mean, the community calls it weak ETH. Strong ETH means eigenstate determinalization is satisfied for all eigenstates. Now, it's not surprising that this can happen, right? For example, I'm sure that all of you are familiar with the physics of localization, of Anderson localization, right? So you know that in Anderson localization, there is a mobility edge, and states here are localized, and states here are delocalized. And eventually, when this closes, you have the Anderson transition. Now the question is, in the context of ergodicity, delocalized states are the equivalent of ETH states, in a sense. So the question we could ask is, well, what do I need to have a mobility edge? Can I have a situation in which I have a localized state that is sitting within the continuum of delocalized states? Yes, you can, but there's nothing forbidding it. But why you never bother to discuss this situation? Not only because it's only one state, but because they are not stable. The moment you change slightly your potential by a tiny bit, these guys will immediately hybridize with a continuum of delocalized states and become delocalized as well. Eventually, a localized state will appear somewhere else. Well, the scars are something similar. You need some very fine tuning in order to observe scars within a continuum of ETH states. But the moment you perturb it a bit, your system, the scars immediately hybridize with the rest of ETH states and become ETH. So it's a similar physics. All right, so I think we're done. So we'll meet after the break for the second part.
Thank you.